In the last video, I said that a lower boiling point solute is going to travel faster through a column than a higher boiling point solute. While that is true, it is not the entire story. There are quite a few factors that affect how quickly something elutes through the column, but we are only going to cover the major two, the first of which is actually boiling point. So let's write this down. Major two factors for elution time. Major two factors for elution time. First is boiling point. Or BP. Lower boiling point means faster flow through the column, thus a lower or smaller retention time. Let's write that as follows. Lower BP means faster flow through column, faster flow through column, which means lower retention time, or T subscript R. A general rule of thumb is that a smaller compound will have lower van der Waals forces, which is a term you might remember from general chemistry. We won't go into it, but the bottom line is smaller compounds tend to have less of these van der Waals forces, causing molecules to be attracted to one another, and thus it's easier to vaporize them into a gas. Now, the other major factor that we will consider is polarity. When I say polarity, I'm talking about both the solute and the stationary phase of solute and stationary phase. You probably remember learning the phrase like dissolves like. Well, let's use a different phrase. Like interacts with like, which is actually the key to one dissolving the other. So, like interacts with like. Applying that version of the phrase, what we can say is that a polar stationary phase interacts with a polar solute more. Polar stationary phase interacts with a polar solute more. Interacts with polar solutes more. Again, like interacts with like. So just imagine that our column is coated with some kind of polar liquid, and then if we were to put two different solutes in with, say, the same boiling point, but what differentiates the two is polarity, one's nonpolar, the other's polar, that polar solute is going to interact with these polar walls a lot more than the nonpolar, and thus it's going to travel significantly slower, right? That's what determines the speed of a compound. How much does it interact with the stationary phase? Two things that go into that, boiling point and polarities. Are they similar or different? I'll finish the notes on polarity by just rewriting that phrase but replacing the word polar with the words nonpolar. So I'll just write quotes, nonpolar stationary phase interacts with nonpolar solutes more, end quotes. Now let's see the interplay between these two factors with an example. Starting with the chromatogram on the right side. This one's easier to make sense of. So in this example, a mixture was run through a column that had a polar stationary phase coating the inner walls, and the mixture consisted of 10 different compounds. And at first there seems no rhyme or reason to this ordering of compounds, so let me organize it in my own way. Compounds 2 5, 8, and 10 are all nonpolar, each one bigger than the last, thus each one has a higher boiling point than the last. And we'll color code those compounds as blue. And then compounds 1, 4, and 7, which will be purple, are intermediately polar. And once again, they are organized in order of increasing boiling point from one another. And finally, in red, compounds 3, 6, and 9, very polar, propanol, butanol, pentanol, each one getting larger than the other, each one having a higher boiling point than the other. Now let's look at the chromatogram itself. We can see that in this case, the polarity differences really help separate our three categories of compounds from one another. All of our nonpolar compounds elute first in order of increasing boiling point. Then the intermediately polar solutes come out next, again in order of increasing boiling point. And finally, the strongly polar solutes make it out in order of increasing boiling point. So here the polarity discrepancies really make a major difference, and then the boiling point determines the order of elution within those same polarities. Notice that even though octane has a significantly higher boiling point than, say, acetone, it still comes out before acetone, but only a bit before. So at some point, the boiling point could be so high that it more than makes up for the difference in polarities. So there is an interplay. Now when we look at the chromatogram on the left side, we have the same mixture being run through a column with a nonpolar stationary phase. And here everything's more jumbled together. What is still true is that compounds that have the same polarity still clearly elute in order of increasing boiling point. Here's our intermediates. Lowest boiling point, medium, highest. Of our polars, lowest, medium, highest. But as far as the polarity differentiation goes, it's not as clearly split up as over here. Everything's kind of jumbled together. The differences are not as striking, and that's presumably because the interactions between nonpolar solutes and a nonpolar stationary phase are not as strong as the interactions between polar solutes and a polar stationary phase, so you don't get nearly as much of a division between everything. But we can still make some clear observations. For example, propanol, which is number 3, and heptane, which is number 8, have roughly the same boiling point, 97 and 98, basically the same, but because it is nonpolar, it is retained longer by our nonpolar stationary phase than the polar propanol. Another clear observation to make is that our nonpolar pentane has a lower boiling point than our intermediate polar acetone, and yet the pentane, despite having a smaller boiling point, still comes out at a slightly later time than the higher boiling point acetone, because in the end, there's that polarity match. And so the two factors that were discussed are still very much in play in this column. However, it is not nearly as obvious to see as in this column.